So on this first example, again, we're just graphing these constraints or these inequalities. So first, let's start off with, in my mind, what should probably be the easier two to graph. So the line y equals 6, what kind of line is that? What is that way? Horizontal. So it's a horizontal line at 6. The line x equals 1 is what?
Vertical.
It's vertical where x is 1. Now, let's talk about graphing these first two. Okay, I'm going to show you a different way to do it than having to put it into y equals mx plus b, finding your y-intercept, counting your slope. Okay, we're going to graph these a little bit differently. We're going to find the x-intercept and the y-intercept. So you're going to have a point somewhere on here. You're going to have a point somewhere on the y-axis. And then you're just going to connect the two. So on this first example, well, one, x-intercepts. What do we know about x-intercepts? What is always true about it? Chance, what is always true about an x-intercept? The y value is always 0. What is always true about a y-intercept? The x is always 0. So you're going to use that information about it to find the x-intercept and the y-intercept. So first on the x-intercept, I know the y value is 0. So on that first equation, I'm going to plug 0 in for y. Now, whenever I'm solving this, I'm just going to use equal to. I won't use the inequality, just for solving purposes. Okay? 5 times 0 is what? So that's what I'm left with. So what is x going to equal? 10. So my x-intercept is 10, 0. Then I'm going to do the same with the y-intercept. But I'm going to put 0 in for x. 4 times 0 is?
0.
So I've got 5y equals 40. So y equals what? 8. Thank you. So now I'm just going to graph those two. So I've got the point 0, 8. Right about there. I've got the point 10, 0. Right about there. And I'm going to connect the two. Now, an easy way to speed up that process, and I don't think it really makes the work any harder or more complicated. In fact, it might make it easier. On this second equation, finding the x and y-intercept. If I want to find the x-intercept, I'm going to completely ignore the y term, because that's what I'm going to plug 0 in for, and it's going to cancel every time. So I have 2x equals 20. So what is my x-intercept? 10, 0. Same thing for my y, but now I'm just going to ignore that x term. So I'm left with 5y equals 20. So what is my y-intercept? Do what, Garrett? 0, 4. So I've got 10, 0, which is already graphed. It's coming from the same spot. And I've got 0, 4. Okay. After that, let's talk about shading. Now, I don't want you to shade yet. So here in a minute, I'm going to be shading up here. I don't want you to fill that in yet. We're going to do it, and then I'm going to talk about how I do it a little bit differently than I know some teachers teach it. So if I was to shade this first equation, which is my 10, 0, 0, 8 line, the inequality is less than or equal to. So where would I shade on that? Above or below the line? Below. And again, do not shade right now. I'm just kind of explaining why I don't do it this way. So I would shade below that line, which is all that. The next one, my 10, 0, 0, 4 is greater than. So would I shade above or below that line? Above. So I'm going to shade everything above that line. There it all is. Okay? Y is less than 6, so would I shade above or below that line? Below, because it's less than, right? So common knowledge would tell me to shade that, all that below there. And then x is greater than 1. Now whenever it's an x equals line, you got to think a little bit differently. Don't think above and below, think to the right or to the left. So if x is greater than 1, are the numbers greater than 1 to the right of that line or to the left of that line? To the right. So I'm going to shade all this again. And now my graph is shaded, so I got to find my answer. Okay? So hopefully, maybe you can see why I don't do it this way. And I did it all in gray, because usually do it in pencil, so your graph would look roughly like that, had we just shaded it like that. So whenever I shade it, I'm going to shade it opposite the sign. So now we're all going to go through here and we'll all shade this. So going back to my 10, 0, 0, 8 line. The sign is less than or equal to. So if I shade opposite, am I going to shade above or below it? Above. So I'll take it right here. So go ahead and shade this with me, please. Everything that is above that line I need to shade. Okay. After that, this is my other line that's slanted, the 10, 0, 0, 4. The sign is greater than or equal to. So which am I going to shade above or below that line? Below. So it's just that bottom left corner area. Okay. After that, the line Y is less than or equal to 6. Above or below? Above. Which is just this little, the part that's not shaded yet is that little triangle on the left. Okay, and again, these x equals the vertical lines. Make sure that you're careful with these. X is greater than 1, so do I need to shade to the left or to the right? The left, which is just, looks like those two little squares. Okay. So now, the area that I'm going to focus on, which is what is going to be called what is called the feasible region, this is where I'm going to get my answers from. Okay, and as you can tell, I can identify the feasible region, shading it that way a lot easier than the other way. All right. Now, to get these answers, we have to go through and find the vertices. Vertices is a fancy word for
Vertex.
Not vertex, which that makes sense. But vertices is just multiple vertexes. But don't think vertex like the absolute value that we just found, or whenever we get to quadratic. Think more geometry. A vertices is a what of the shape? Corner point. Okay? Or if you're looking at the lines, it's where the two lines are going to be crossing. Okay? So we need to be able to identify all of the vertices of that feasible region. So looking at all of those, Zach, what is one of the vertices?
1, 7.
1/6. Gracie, what's another one? 10/0. Okay. And then we'll do 2.56. Which is this one. And then let's do 3.5. Okay. Now, on a lot of these kind of problems, you won't see a lot that are decimals. This one's just kind of the way this one works out. The majority of them it'll intersect at two whole numbers. Okay, but you can see the importance, why I made sure all of you had rulers, the importance of graphing these accurately. If one line is off a little bit, your vertice is going to be off. And then with what we have to do with those, then the whole problem just kind of will not work out. Okay. So whenever I graph it, my feasible region is always going to be the unshaded region. If you have a graph and that feasible region is given to you, it's printed, it looks all nice and neat and everything like this example 2, the feasible region is going to be the shaded region. Okay, so that might cause a little bit of confusion, but no, if you are finding it, shade opposite the sign, it's the unshaded. If it's given to you, the problem is trying to draw your attention to the shaded region. So we need to find the vertices of this. So Olivia, will you give me that vertex, the top left? Andy, give me the top right. Isaac, give me the bottom right. And Morgan, give me the bottom left. Olivia, do you have yours?
-3, 5.
Fabulous. 1, 5.
6 and -2.
Awesome. So just make sure you can identify the vertices. That's all that problem is really talking about. Be able to find those corner points and identify them. Okay. So what we will end up doing with those vertices is we're going to put them into something that is called the objective function. This is what you will use to find the maximum or to find the minimum. Okay? And again, the maximum may be profit. That's probably the most common example. If you're trying to minimize the cost of a company that's making something, that's another example that you may see. So if you look, let's use that objective function. So again, we'll need to identify these vertices first on the next page. So, Ryan, what are one of the vertices on that one?
4, 4.
4, 4. Gracie, what's another one?
1, 1.
1, 1. Aaron?
1, 8.
And Trey?
4, 8.
Okay. On this specific problem, the objective function is given to us. Okay. It will not always be given to you. Sometimes you'll have to find it. Do not try to graph the objective function. Ever. Okay. In the past, I've had a lot of people, they'll graph the constraints and they do it all correctly and they shade it correctly, and then somehow they try to fit that equation into it. Okay, do not do that. The objective function, always start it with P equals. Okay, so something that has worked for some kids in the past. Just make sure you don't graph the one that has the equal to in it, okay? Because then you wouldn't be shading. Everything you graph on here, there's going to be shading involved with it. So, once you find the vertices, and this is where the work gets extremely tedious, you will plug every point into that objective function and see what it equals. You got an x and y on each coordinate point. You plug the x for x, y for y, and then see what P equals. So on this particular one, you're going to have P equals 3 times something plus